Today we're going to talk about double angle formulas. Important. Trigonometric identities are equations that are true for every value in the domain. So I'm going to give you a general example for that. If I say everyone in your class is 17 years old, then that has to be true for every person. That's an identity if it's true for every person. But an example is not equal to a proof. If I picked one of you and said, are you 17? Yes. That doesn't prove that everyone is 17. One example isn't the same thing as a proof. You've got to prove things in general terms, not simply by subbing in a value or picking one student. A counterexample, though, can be used to show that it's not an identity. So if I talked to a classroom full of students and said, everyone here is 17 years old, and then one of you raised your hand and said, well, I'm 18. Then that's all we need. That's a counterexample, and I only need one of those to prove that my whole statement is not true. So to prove something is true, we can't just sub in a value. We can't just pick one instance. It has to always be true. Use the compound angle formulas to prove the double angle formulas. So our last lesson was compound angle formulas. This is a double angle formula, and this is one that you're going to add to your list of formulas that will be provided for you, but you need to reference them all the time, so you need to add this one down. But first we're going to start by proving it. So to prove it, let's look at the left side. The left side is just sine 2 theta. And I'm picking this because I can take that sine 2 theta and rewrite it as sine theta plus theta. That's the same as 2 theta. Now you can go back to your formula from our last lesson, the compound angle, and you're going to find the addition formula for sine, and you're going to write it all out and sub it all in there. So go ahead and do that. Press pause, go back to your compound angle formula, find the right one, and fill it in. And you're going to use theta all the time. This is what you should have, sine theta cos theta plus cos theta sine theta. Those two are the same. They're just in the wrong. That's a sine times a cos. That's a cos times a sine, which is like x times y or y times x. It's the same thing. So we have 2 sine theta cos theta. So there's the proof of this formula here. We got our left side to equal our right side. Sine 2 theta, we got it to equal the right side. So that means this is one of your new double angle formulas. Double, right? Sine of 2 theta equals 2 sine theta cos theta. So that's a double angle formula. And we're going to have questions where we need to break down angles into single or to make them from double to single and so forth. So this is why we need double angle formulas. You'll see why. So that's the proof of the first one. Now we're going to prove another double angle formula. So this is another one. For cos 2, this one was what is sine 2 theta? What's this double angle equal to? And now we're going to do cos 2 theta. I want to prove that it's equal to this. And these look really different from each other. This one has squares in it. This one just has a double in it. So here's a strategy. We're going to start with the left side, which is just cos 2 theta. And I'm going to break it apart like I did for the last one. So for the next line, I want you to find your addition formula, your addition compound angle formula for cos, and sub in. Done? Okay. This is what you get. Cos, and you can see how it's going to equal the right side. Up here you can see how we're really there now, because cos theta times cos theta is cos squared theta, and same with sine. So what we started with, cos 2 theta, we got it to equal the right side. Our left side is equal to our right side, so we've just proven this double angle formula for cosine. So we've proven 2 of them so far, so you're adding these 2 onto your list. There's 3 double angle formulas for cosine actually, and we can derive them in different ways, but we'll find another one here. We're going to start with the one that we just found. We just found this double angle formula, but what I'm going to do is just look at the right side. The right side is cos squared theta minus sine squared theta. Just look at the right side. Now we want to go back to an important identity from grade 11. The Pythagorean identity says that cos squared theta plus sine squared theta equals 1. That comes from the Pythagorean theorem. X squared plus y squared equals 1. And we're going to isolate for sine squared. I mean, we're going to take this cos squared and bring it over to this side here, and then sub in. So I put that in this kind of green color here. Instead of sine squared, I'm writing that as 1 minus cos squared. Let me just be clear on what I did here. I took this formula, I took the cos squared, brought it over here, so that left me with sine squared equals 1 minus cos squared. So instead of sine squared, I put in 1 minus cos squared. Okay, so then we've got that. Now I'm just going to drop off the bracket. When I drop off the bracket, of course, we have to distribute the negative in. And that gives us a negative 1 and then a positive cos squared. So these are like terms. They're like terms because the exponent and the variable match. They're both squared thetas, cos squared theta, so they're exactly the same. That gives us 2 cos squared theta minus 1. And that is our next double angle formula. So when we have cos 2 theta, there's another double angle for cos. It's equal to 2 cos squared theta minus 1. And we just got that from the one we already found. So we just took the one we already found and we rearranged it and did something with it to get another one. There's actually 3 of them. We're not going to go through all 3 of them, but the third one can be found kind of using the same strategy, just taking one of your original ones and rearranging it. Let's do an example. Express as a single trigonometric ratio. So this question isn't about a proof. I don't have a left side, right side here. I just have an expression, one piece. So I don't have to try to make it look like anything. But the question is telling me I want a single trigonometric ratio. Right now I've got a sine there and a cos. So I don't want a sine and a cos. I have to just use one of them, either sine or cos. So go back and look at your formulas for today and find one that kind of looks like this. It has a sine and a cos together, sine times cos. Hopefully you found this one here. This was our first one. This is our first double angle. Sine 2 theta equals 2 sine theta cos theta. Now it's not the same, but it's very similar. So what I do is I look at this formula here, and let's first look at the angles. So the sine is the same, the cos is the same, but the angles are a little bit different. I have a 3 theta up here and just a theta here. So what I want to do, I just want to make the angles match. I want a 3 theta, not a theta. So that means wherever I had a theta, including here, I have to replace it with a 3 theta. So what I'm going to write here, let me pick a darker color, is sine of 2 theta. But instead of theta, remember I'm replacing that 2 with a 3 theta so that I can try to get it to match. And I'm going to replace these ones as well. 2 sine 3 theta and cos 3 theta. Remember what the original question was, expressed as a single trigonometric ratio. So I took this one that has 2, it has sine and cos, and I went and looked for something I already have from today that has a sine and cos, but has it equal to a single trig ratio like this one here. So that's why I'm using this formula. So first thing I'm doing is just getting the angles right. So what I have here is sine 6 theta. This is really sine 6 theta equals, and then this stuff I can't change anything here. I'm just going to leave it, just drop the brackets off. Okay. But I want it to look like 4 sine, so I'm really close. See, I've got the sine 3 theta, cos 3 theta, I've got this part done, but I don't have a 4 in the front. So if I want this original one that I started with here, I don't want a 2 in the front, I want a 4 in the front. I'm going to multiply both of these sides by a 2. So that keeps this equation still balanced, still true. But if I multiply this leading coefficient by a 2 and this leading coefficient by a 2, that will give me the 4 I need there. So my next step is to take this whole expression right here, both sides, and multiply it by 2. Multiply both sides by 2. That's going to give me 4 sine 6 theta equals oops, not 4, sorry, looking ahead, 2. 2 sine 6 theta equals, here's the 4, sine 3 theta, cos 3 theta. And that was the original question. The original question said, take this expression right here and rewrite it using just sine or just cos. So I've done that. Here's the same thing. I'm putting a black box around the same thing. I've got the same part here, and I managed to rewrite it as a single ratio. So the single trigonometric ratio is really all I really need to write here is my answer, which is 2 sine 6 theta. That's what it's equal to, the part that's in black. So your strategy with these types of questions is to look at what you have and think, what does this resemble? I'm going to go back and look at my formula sheet. What does this resemble that is equal to a single trigonometric ratio? So you're looking through what you have to find something that you can manipulate. We'll try another one like that. This one says evaluate, though. Evaluate means when I'm done, my answer is going to be a number like 12. Right? That's what evaluate means. Evaluate this. This is really messy looking. And it says exact values only. It means I can't use my calculator anyway on my evaluation for this chapter in my class. So I've got to figure this out without getting out my calculator. First of all, this is pretty messy, and without my calculator, I can't calculate this. So I'm going to have to look again at my formula list and say, what does this resemble? Just this piece right here. Now I know I have nothing with a 5 pi over 12, but I'm looking at the general layout. I've got a cos squared of an angle minus sine squared of the same angle. These are both the same, 5 pi over 12, 5 pi over 12. That's the same angle. What does that resemble when you look through what you've got here? Hopefully you found this one. It resembles cos squared of an angle minus sine squared of an angle. So this is really similar to this piece here. All we have to do is swap out some stuff. So my angle right here, instead of a theta, is a 5 pi minus 12. So I have to do the same thing with this theta. I'm going to have to change that. So let me rewrite the question here first. Let me first rewrite the question. The question was cos squared 5 pi over 12 minus sine squared of 5 pi over 12. So that's equal to, so I'm going to take this piece right here, but I'm going to change my theta. That's equal to cos, there's my double angle, but instead of theta, I have to use the same theta that I did in the rest of the question, which is a 5 pi over 12. So I'm trying to evaluate this question, but this is too hard for me to do. I'm going to use a double angle formula. This would be much easier for me to evaluate than this. This is really difficult. So I would rather switch it to something that I can work with. Back to the right side here, let me just change colors. This is equal to cos, now 2, this is like a 2 over 1. So I'm doing 2 times 5 pi over 12, which is 10 pi over 12, but I'm going to write that in reduced form, which is 5 pi over 12. Whoops, 5 pi over 6. That's my second mistake today. 5 pi over 6, sorry. Now I can do that. I have a triangle for that. Triangle. Here's a right angle triangle. And this will be my pi over 6 angle here. This is my pi over 3. And some of you I know are still converting to degrees all the time. You can do that if you want to. My side lengths, the shortest side is a 1, the hypotenuse is a 2, and the adjacent side here is a root 3. I'm looking for cos of 5 pi over 6. So my angle is a 5 pi over 6, not a pi over 6. So this is the related acute right here. 5 pi over 6 is related acute. So I'm going to find pi over 6 first. Cos of pi over 6 is, remember it's adjacent over hypotenuse. So that's going to be root 3 over 2. But that's not 5 pi over 6, so I need to put this in the right quadrant. What quadrant is 5 pi over 6 in? 1, 2, 3, 4. So I want to take that pi over 6 and I want to put it in the right quadrant. What quadrant does it go in? 5 pi over 6. Remember that 180 degrees is pi. And pi is the same. In this case, we're using a denominator of 6, so I'm going to write that instead as 6 pi over 6. So if rotating all the way to here is 6 pi over 6, then 5 pi over 6 is just short of that. So I'm going to put 5 pi over 6 right here. There is 5 pi over 6. And our related acute is the pi over 6. So in quadrant 2, cos is negative. So my answer to this question up here, cos of 5 pi over 6, we already got the root 3 over 2, but that's got to be a negative because it's in quadrant 2. So there is my answer to the original question, which was pretty messy looking, but using our double angles, we managed to make it a lot more simple, something we can work with. Moving on, here is a list of all of your double angle formulas that will be given to you. You don't have to memorize them, but you should have them written down somewhere. The double angle formulas for sine, that should be on the same line there, sine 2 theta, cos 2 theta, and tan 2 theta. The double angle formulas are quite useful for solving trig equations, and they arise frequency in applications of trigonometry. So we are often looking to swap one out for the other. We're always looking to switch these back and forth in between left side, right side, and picking the one that fits best for the question. Example 3. Evaluate 2 tan 165 degrees over 1 minus tan squared 165 degrees. I didn't really talk about the domain that was on the last question, but the domain is just there to tell us that we're only looking for an answer, even though there's always an infinite number of answers, because these functions repeat, they have a periodic. We only need to find the answers that fit in this space, in this domain here. Okay, remember, no calculators. So I want to evaluate this without a calculator. Do I have a triangle for 165? What is all this mess down here? Well, remember your good strategy for today. Does this resemble something that is simpler? Does this resemble something that I can use? So let's look over here. There's only one possibility. It's right here. This looks a lot like that. All I need to do is take my thetas and replace them with 165s. Other than that, it matches exactly. So I got to take this theta. Let me just draw some lines here. These 165s that were in the question take the place of these thetas, which means this theta as well, not the 2, just the theta has to be replaced with a 165 as well. So I'm going to rewrite that as, tan. So I'm using this piece here. Let me erase that. I wrote over it all. That's equal to tan of 2 theta, except instead of theta, it's a 165. These two are equal to each other because of this formula right here. Okay, I can multiply 2 times 165, that's 330 degrees. Tan of 330 degrees, let's see if we can figure that out without a calculator. I'm going to do a quick sketch here. I'll put it over here. 330 degrees, where is that? 90, 180, 270, and that's 0 or 360. So 330 degrees is going to fall in quadrant 4. So if I drew a terminal arm here, I'm not measuring any of these, I'm just getting in the right quadrant. This rotation would be 330 degrees. Now let's turn it into a triangle like this. There's my right angle. And what is this acute angle tucked into the corner at the vertex here? What does that measure? If the whole blue rotation is 330, if I went all the way to the axis, it would be 360. That means this is 30 degrees in the vertex here. This is 30 degrees. This angle is 30 degrees. I do have a triangle, a special triangle, a reference triangle that has a 30-degree angle. 30 degrees is the smallest side of that smallest angle, so opposite the smallest angle is the smallest side, that's a 1. 90 is the largest angle, 2 is the largest side opposite that, and that leaves me with a root 3 right here. So what is tan of 330 degrees? Now this time I've already drawn it in the right quadrant. For the question we did before this, we had a pi over 6. I didn't start off with the right quadrant, so I then had to put it in this quadrant. This time I drew it in the right spot. So 330 degrees is drawn correctly. I need some positives and negatives. The x value is a positive, but the y value is a negative. And we're looking for tan, remember, and in quadrant 4, according to the cast rule, tan is negative. So my answer, tan of 330 degrees, is equal to -1, that's the opposite, over the adjacent, which is root 3. And that's not rationalized. I need a rational denominator, so I'm going to multiply by 1. And my 1 looks like that, so that I can get rid of the radical sign in the denominator. I get negative root 3 over root 3 times root 3 is, of course, 3. So that is the answer to this very original, complicated looking question. We managed to use a nice formula to swap out the complexity of it and make it easier to work with. Example 4. Determine the value of sine 2 theta given this tan value. And look at our domain here. This is a different domain. Pi over 2, between pi over 2 and pi. What quadrant is that? Pi over 2 to pi. So we've got, here is 0, this is pi over 2, 3 pi over 2. So we're only looking for an answer in this quadrant right here. This is the only place our domain exists, so we don't have to worry about any other answers. Very specific domain this time. Determine the value of sine 2 theta given tan. Now one of my main strategies I've been using so far is what can I swap out? Can I simplify something by using one of these formulas? There's no formula up here with a single tan. This is actually quite simple looking as it is. I don't have any double angles. I don't have any powers of 2. I don't have multiples, sine and cos, or multiple ratios. I just have a single tan. So this is already pretty straightforward. But how am I going to get sine 2 theta when I'm given tan? So let's talk about what we have here. I'm going to erase this and just write it a little tidier. So let's put this on the axis here. Tan, remember tan is y over x, or opposite over adjacent. So I'm going to draw this on my graph. So I've got a negative here. Y is 7, x is 24. One of them is negative. Which one? Remember, we're in quadrant 2. What's negative there, x or y? So it is the x that's going to be negative, because in quadrant 2 my x values are negative. So let's go over here. Let's say right there is negative 24. And then 7 would be, that's not to scale, of course. 7 is about here. Well, I'm going to put let me erase my quadrant 2 there. I'm going to put a dot right here where I think my value is. So I'm going to draw a terminal arm right through the origin and that value, negative 724. So everything's matching so far. I'm in the proper quadrant that the question told me to be in, and I've got my negative sign allocated down here to the x value. Just erase this stuff here. So my triangle, let's drop a perpendicular line down. There's 90 degrees. So this side, this is 24 right here. This is my negative 24. This side here is positive 7. To find sine, the original question asked me for sine 2 theta. I'm going to need the hypotenuse or the radius. So we'll go to our Pythagorean theorem. X squared plus y squared equals r squared. Or a squared plus b squared equals c squared, whatever version you want to use. So we're subbing in. Our x is a negative 24. Our y value is 7. And that's equal to r squared. So these numbers, you're not permitted a scientific calculator, but I will give you a basic calculator that allows you to do multiplication. So you could do this on a basic calculator. Negative 24 squared is 576. 7 squared is 49. And that's equal to r squared. So we get 625, and that's a good number. Some of you, I think, would recognize that, r squared. To isolate r, I take the square root of both sides. And our radius or hypotenuse can only be positive, so I don't have to put a plus or minus in front because r is never negative, it's always positive. Square root of 625 is 25 equals r. So now I have a value of r. Let's put it up here, erase this r and put my 25 here. That's 25. So I've got all my values. I'm trying to find sine 2 theta. For sine 2 theta, so I've got an x value. I'll write it out again here. I've got x equals negative 24, y equals 7, and of course we already figured out r is 25. Now that we have all of these, we can find sine, cosine, tan, because sine, cosine, tan are just different ratios of these three numbers. So for sine 2 theta, I go up here, sine 2 theta, we're going to use this formula. Sine 2 theta equals 2 times sine theta times cos theta. And I'm trying to find sine 2 theta. So 2, what is sine theta? Sine theta is, remember that sine is opposite over hypotenuse, or y over r. So in for sine, I'm going to put 7 over 25. Cos is adjacent over hypotenuse, or x over r. So cos is negative 24 over 25. Now, see that I don't know what theta is. This is really my principal angle here is theta. This is my related acute, and here is beta. I don't know the angle, and it's not asking me for the angle. So I don't need to figure out the angle because I know x, y, and r. I know the side length, so I don't need the angle. So now you do some math here and you multiply. So this is really 2 over invisible 1. So we multiply straight across the top. All those three numbers are going to give us negative 336. Straight across the bottom, 25 times 25 is 625. So that is your answer for sine of 2 theta. That was the original question, find sine of 2 theta. I had to use this double angle formula up here because I couldn't sub in any angle. I don't have a double angle for sine 2 theta, so I had to go here to the single angles because I could use all of this stuff with my single angles. Okay, so that is the end of the lesson on double angles. Make sure you've got a good formula sheet going there with all the stuff that you need, and you reference back to your formula sheet as you do your work. Good luck.